Good evening, sir. This is my today personal timetable. Um, as you said, I have to present uh, thesis. I have gone through your all comments and I have keep that comments in my mind. According to that comments, I have made this presentation and just have a look on it. The first theory thesis name is radiometric thermometer for variable deep tissue monitoring. In this chapter 2 was temperature retrieval. Now, what is the temperature retrieval? It is a uh, it's like a in reciprocity. Reciprocity is between the emission and absorption is well known in case of far field radiation, and it's for black body the radiate and powered and absorb powered are equal, and simulating volume power loss density in the body due to transmitting probe on the skin can predict the emitted power from the volume received by the same probe. Now I'm going to explain this figure. In this figure, there is a small probe. What is this probe? Probe is like for measuring. Is a measuring element, and it is in this figure. Probe is placed on the top of tissue, and a small current element I is in the tissue. There are two set of source like JS and JI. JS and JI are radiating inside the tissue at the same frequency and producing the electrical field of ES and EI respectively, and it will produce ES and EI. The length of both radiator now length LS and LI are short, forcing a uniform electric field on the probe. And now I'm going to explain this in this figures in this four figures, the how the network travels and internal current element, and how we can and how the current element receiving mode and transmitting mode happens. In as you can see in this figure, first there is an equivalent network for internal current element that is in receiving mode, and in the second figure, as you can see, the impedance of the internal current element, that implies Zi, is assumed to be conjugate of the impedance of the load, the internal current element in receiving mode. And as you can see in this figure C, this is equivalent network for internal current element in transmitting mode. The small probe, uh, in in figure D, you can see there is a small probe in receiving mode. Uh, that is the internal impedance of the main probe. ZS is assumed to be conjugate of the impedance of its load. And in this figure, there is an how the power is delivered, and in the thermal equilibrium, all this happens in this figure. uh, as you can see in this first A figure, the power delivered by current element placed inside a closed system at thermal equilibrium enclosed of temperature T, and in the B figure, power is equal to the power delivered by resistor. The resistor is R Ri, maintain at the same temperature, assuming each is connected to a matched receiver of bandwidth B. And in figure C you can see there is a equivalent voltage of a black body radiator. The internal current element impedance Zi is assumed to be the complex conjugate of its load impedance. Therefore, it is shown by the respiratory, the thermal noise power delivered by a tissue at a non-zero temperature at a near-field small probe is directly proportional at the observed power by the same tissue volume delivered by the same probe in transmitting mode. And in this chapter I have learned that there are various method for temperature retrieval. Now the power is measured by a radio. A model is needed for a tissue stack to determine the temperature distribution. And the first method is finding the partial green functions. Now, in what partial green function is solved for a simple isotropic dipole located in a cavity and comprehensive partial temperature profile of head model is presented. This method can be easily extended to complex non-homogeneous media in direct contact with a complex probe. And the another method is multi-frequency radiometer to find the temperature profile of different tissue layer. Method required multiple radiometer, which is in turn increase the size, power, consumption cost, and complexity of the system. It is less accurate when weighting the function of deep tissue layer, and the data analysis is not so retrieval, become sensitive, and it can become sensitive to many unknown parameters. With these theories of two frequency near field microwave probing of planar static media with measurement of water, glass, water phantom, I is investigated in quit frequency of 1.4, and the quint frequency ranges from 1.4 and to 2.7 gigahertz. And the third method is like molding the temperature profile with bioheat transfer equation. Combine in this uh, in this method, combining the knowledge combining the two above both method like multi-layered radiometry and bioheat equations, and that can provide a partial temperatures, uh, and this advantage in help of improving the accuracy and provide a partial temperature profile. It also gives the data of it gives more information about heat rate, heat exchange, blood fusion, blood heat generation, which is not easy to obtain for different people under different activities. And now uh, in this chapter, another topic was radiometer buried layer thermometer calibration. Now, a thermometer calibration consists of two: instrument calibration and model calibration. In instrument calibration, uh, is like it corrects the gain of fluctuations of the radiometer, and in model calibration, it refers to a near field EM analysis as well as reflection loss and mismatch in the system. I'm going to explain this figure, which I have mentioned over in this presentation, and it was in the thesis also. So I'm going to explain this. Uh, uh, as you can see in this figure, the setup of radiometer placed on layer 1, on the layer 1 with other tissues, like on layer 1 there is a skin, and on layer 2 it's fat, muscles, and and etc. uh, uh, and the radiometer receive the radiation through the probe, which is not a which is at physical temperature, and physical temperature denotes the symbol TP. TP is a you can say as a physical temperature, and in total power received from the tissue stack correspond to a probe radiometric temperature T equal to P equal to KB. Therefore, the equivalent thermal noise temperature of issue tag, each tissue layer at different temperature, it and it and each tissue will define different temperatures, and this temperature contribute to each layered of the factor, and there is W1 and 2. It's like weight of the tissues layered by a factor. You can denote as a Wi, as a Ti is the physical temperature of the ith layer, and is the ith layer of weighting function, and in this figure you can see that and this whole figure has a noise free radiometer, and depends on the frequency, thickness, conductivity. Thickness symbolized as D, conductivity, and near field pattern of the probe. Functions Fn. Um, Now I am going to summarize this thesis. In this thesis, uh, the interactions of human tissue layer with a probe and calibration procedure for a microwave thermometer. In this thesis, I have learned about the background of temperature retrieval, and I have described previously also there were three methods, and how to retrieve temperature, and for and next was the reciprocity with the radiate and observe thermal noise power density in the near field tissue layer, as discussed in the previous slide. And next was the measure radio temperature is formulated as a summations of contribution of each tissue layer, their physical temperature and required device calibrations shown to be function efficient of probe, cable loss, gain, fluctuation of radiometer device and probe bandwidth. And this is my second thesis. The name of this thesis is a microwave radiometer for internal body temperature. In this also, the chapter 2 was radiometer design. Now I'm going to explain this figure as you can see in this presentation, is a simple block diagram, which is a power radiometer along with important parameters such as G, which is gain, and bandwidth B, and you can see the power is detector with a square law detector x square, and integrated with an integration time t. Now in this G is in simple terms, power is received through an antenna at an equivalent noise temperature, which is T complement A, and gain is G, is dedicated by a number of amplifier in the receive chain, and loss in the receiver from passive elements such as transmission line and filter. And now what is now in this block diagram, bandwidth is generally detected by the filter used in production section of the receiver. uh, but the function of bandwidth was active components such as amplifier and a square law detector. And now after this all process, the output of this block diagram is integrated with time constant t to improve the radiometric solution. Ah, in this design, radiometric design, another figure shows was in that thesis was equivalent noise temperature definition, where the noise device. As you can see, there is a two figure, uh, figure A and B. First figure determine is a uh, terminated in a fiction with 0K load is replaced by a noiseless device. Now in figure B, as you can see, terminated in a resistor R with an equivalent noise temperature. Now I'm going to considering these two networks. Uh, in first, I'm explaining you this first figure, that is 2.A, is a noise amplifier with fiction 0K load at input such that PNI is equal to 0. And for this case, piano presents the output noise power generator by the device when the input is connected to the noise free termination. This network is replaced with the equivalent noiseless network as shown in. As you can see in the next figure B, there is a TE represent, that is an equivalent temperature of match resistor referred to an input of noise free device that will generate a same output power PNO as in um, figure 1, but the value is different. Now I'm going to explain the receiver architecture. As you can see in this block diagram, uh, there is a now what is the receiver architecture is a total power radiator, total power radiometer, and to reduce the effect of gain variation, they proposed a radiometer that is periodically compared to a matched reference load at a stable temperature T reference, as you can see in this figure, and the output is synchronously demodulated, and and the next architecture of received is was there receive there was there is many architectures, receiver architecture like DIC, radiation balance, noise injection, and two load radiometer. Now I'm going this was the next block diagram that was mentioned in the thesis. um, and I have reviewed this block diagram. In this method for balancing include varying the reference load with a variable attitude until the reference temperature is equal to the antenna temperature. And another method of balancing of radio is to eject a variable amount of noise and from the noise source with the variable attitude by the means of coupler into the antenna part to raise the antenna temperature to be equal to the reference temperature. As you can see in this figure, balancing technique require feedback to control the attitude until a balanced mode of operation is achieved. And that's it for the thesis. Thank you.